Our universe is a vast and mysterious expanse, home to an almost countless number of galaxies, stars, and planets. But where did it all come from? How did our solar system and planet Earth take shape? In this video, we'll take a journey through time and space and explore the incredible history of the universe and our place within it. But to understand how planet Earth came to be, we'll first need a bit of cosmological context. Throughout human history, astronomers, physicists, and cosmologists from around the world have observed a sea of evidence, which has culminated in a theory that explains the very origins of our universe. This theory, commonly known as the Big Bang Theory, explains not only the beginning of the universe, but everything in it, including Earth itself. The Big Bang Theory is based upon a tremendous amount of astronomical and cosmological data that, when put together, provides strong evidence for an expanding universe. Cosmologists, who can calculate the rate of the expanding universe, then run their cosmological models backward in time, are able to calculate a point in time and space about 13.75 billion years ago, from which the universe began. That point in time and space is known as the Big Bang Singularity, or gravitational singularity, an incomprehensibly small point of impossibly high density, pressure, and temperature, in which time and space themselves lose all meaning. The Big Bang was an instantaneous explosion of all matter from this singularity. It would initially have been a massive primordial cloud of subatomic particles. The temperature during this 1 second would have been 10 to the 32 degrees Kelvin, or 100 quintillion degrees Celsius. The ratio of neutrons to protons as we know it today would have been established within the very first second following the Big Bang. Between approximately 10 seconds and 20 minutes after the Big Bang, some of the protons in this primordial cloud would remain as hydrogen, and countless protons and neutrons would fuse into deuterium, the helium isotopes helium-3 and 4, and lithium-7 in a process called Big Bang nucleosynthesis. These primordial elements would go on to be responsible for the creation of all other elements on the periodic table as we know them today. But what does this all have to do with Earth? How did Earth form from this hot primordial cloud of protons and neutrons? At about 24,000 years after the Big Bang, still 13.75 billion years ago, the universe reached a point at which it had more matter than energy, allowing the universe to cool and slow its expansion. At about 370,000 years after the Big Bang, the universe had cooled to about 2700 degrees Celsius. It is during this period of time, known as the recombination epoch, that electrons begin to combine with protons to form stable atoms. This process results in the emission of photons, known as photon decoupling. At this point in time, 370,000 to 380,000 years after the Big Bang, light photons are able to travel freely through space, and the universe becomes transparent. We can still see the remnant electromagnetic radiation from this period reaching us today, known as cosmic microwave background radiation. At about 100 to 200 million years after the Big Bang, gravity has firmly taken hold of the heterogeneity of the universe, and the first stars begin to form. Between 200 million and about 1 billion years after the Big Bang, small galaxies began to form. Plenty of evidence exists to show that our own Milky Way galaxy may have begun to form between 200 and 600 million years after the Big Bang. These images from the Hubble Ultra-Deep Field show some of the first galaxies, thought to have formed as early as 500 to 600 million years after the Big Bang. Fast forward to about 3 billion years in, or about 10.8 billion years ago, and small galaxies begin to merge to form larger galaxies. At about 6 billion years after the Big Bang, or 7.8 billion years ago, the first stars begin to die and explode in what is known as a supernova. The nuclear fusion that occurs within stars, as well as their supernova deaths, is responsible for the creation of all natural elements we find here on Earth, including carbon, oxygen, iron, nickel, gold, lead, uranium, and many others. But we're not quite done telling the story just yet. Our Sun and solar system began forming from a cloud of gas and dust a little over 9 billion years after the Big Bang, or between about 4.6 to 4.57 billion years ago. Our solar system would have formed from the gravitational collapse of a fragment of an interstellar cloud, nebula, or primal supernova within the Orion arm of the Milky Way galaxy. This is commonly known as the solar nebula hypothesis. At around 4.56 billion years ago, our Sun would have taken shape, and the remnants of the solar nebula, a giant cloud of gas and dust orbiting our young Sun, known as the protoplanetary disk, would serve as the nursery to the rest of our eventual solar system. At about 4.54 billion years ago, all of the planets in our solar system began to form through a process known as accretion, the gravitational accumulation of dust particles and gases. Planetary science, which is essentially the study of all celestial objects, can be applied toward understanding the formation of objects as small as meteorites, asteroids, and moons, to terrestrial or rocky planets like Mercury, Venus, Earth, and Mars, to gas giants like Jupiter and Saturn, to the ice giants Uranus and Neptune, and even dwarf planets like Pluto, Ceres, and Eris. 4.54 billion years ago, variations in composition and density across the protoplanetary disk would have led to the gravitational accretion of dust particles. As progressively larger clumps of matter began to attract, a process known as runaway accretion would take hold, leading to the primal core of Earth and other planetesimals exerting a stronger and stronger gravitational pull on the particles and rock fragments around it. Because of runaway accretion, Earth is believed to have been mostly formed within a period of about 10 to 20 million years. This period of time marks the beginning of Earth's geologic timescale, called the Hadean. Chondritic meteorites, one of the most significant pieces of evidence we have for the age of Earth and the solar system, originated as asteroids during this time period. Chondrite, composed of chondrules, or small spherical minerals that formed as droplets of molten rock within the early protoplanetary disk, can be radiometrically dated to measure the age of the meteorites themselves, as well as the ages of their impacts on Earth. As Earth grew in size, its own gravitational force would pull mass into the center, producing an immense amount of pressure and heat. The majority of Earth's volume during this period would have been a molten liquid similar to lava or magma. Of the four most abundant elements making up Earth, oxygen, magnesium, silicon, and iron, being the heaviest, would begin to sink, taking the siderophiles, or iron-loving elements nickel and cobalt, with it, along with other iron-loving elements such as platinum, palladium, and gold. As Earth cooled, its composition would continue to differentiate, with heavier elements continuing to sink to its center, creating a solid core, and lighter lithophile, or rock-loving, elements floating to the surface. Over time, the molten mantle, which takes up about 84% of Earth's volume, began to crystallize into the silicate minerals olivine, pyroxene, and garnet, leaving a molten outer core as the solid lower mantle took form. During Earth's early formation, around 4.53 billion years ago, planetary scientists believe a hypothetical planetoid, or protoplanet named Theia, smashed into Earth, resulting in the formation of our Moon. This high-resolution simulation from NASA demonstrates that the Moon may have formed in as little as a few hours as a result of this massive collision. The gravitational pull of the brand new moon would serve to help stabilize Earth's axis of rotation and serve as the primary influence on Earth's tides. Meanwhile, Earth's asthenosphere and lithosphere, or crust, would have formed quickly and would have continued becoming enriched in lighter lithophilic elements such as oxygen, silicon, aluminum, sodium, magnesium, calcium, and potassium. Convection within the asthenosphere, the ductile, partially molten layer of the upper mantle upon which Earth's crust floats, would become a primary driver of plate tectonics, mountain building, and volcanic activity that would lead to a rise in atmospheric gases and eventually all life on Earth. For more on this and other amazing Earth science topics, stay tuned for another Earth in Depth video. If you enjoyed this video, please consider liking, subscribing, and visiting the links in the description. And if you just can't get enough Earth in Depth, please consider joining our Patreon, where you will get immediate access to our exclusive in-depth videos on all things Earth science. Your support helps us immensely to create more content just like this. Thanks again for watching. We hope to see you again soon.